Hello, so in this video, I'm going to be going over a problem that involves numerous nodes that are connected by pipes, and there is water flowing through the pipes, and we determine things such as the flow rate of each of these pipes. So to start things off, I went ahead and imported all of the functions we'll need, such as numpy as np, which is pretty much Python, and we'll use this Newton and root imported from scipy.optimize later in the program as well. So I went ahead and typed out all of the givens in this problem. We had things such as gravity, which this g is just the acceleration of gravity, which is 9.1 meters per second squared. We have rho equal to 1,000, in which rho is just the density of water. We have mu equal 0.001, which is the viscosity of water. We have this capital D equals 0.1, which we have as the diameter of the pipes. Of all of the pipes, they're all 0.1. And this ED is the relative roughness of the pipes, and we have that equal to 0.001. So what we are first going to do is we are going to have a function to describe the factor of friction. So this F will stand for friction, and what we'll need is this RE. We're going to have this as Reynolds number. So what we are first going to do is we are going to have two parts of this in here, which we are just going to call A and B. So we're going to have A equal to 2.457. And it's going to be times the log. And this NP is from this numpy. So the np.log allows us to take the log of whatever number value we want. And we are going to have this equation as A. So as you can see, we have Reynolds number here, and we have the relative roughness here. And for the second part, we are going to have this B, which just equals 37,530 divided by Reynolds number. And what we want this to return, and I forgot to hit enter after that, so there we go. All right, so we want that to return and we are going to have it return this little expression here. And as you can see, we have Reynolds number in it as well, and we also have A and B being added together here. So now if we hit Shift Enter, there are no errors so far. So now what we want to do is we want to create a function called dHead, which can be called delta head, change in head, whatever. I just called it dHead because it's shorter and easier to type. And what we will need for this will be Q, L, K, D, and ED. And in this, it's similar things. ED is the relative roughness, L is length, etc. And Q is a flow, all of that stuff. So in this, what we will want to do, we will want V equal to the absolute value of flow divided by P dot pi So we want V equal to this equation right here, in which V is the velocity of the fluid. And so one thing to note is this NP dot abs means that the velocity will always be positive. So if you get something negative for the speed, then I don't know what's wrong with the program, but you shouldn't, because everything in this is in the absolute value. And this NP dot pi is again from numpy as NP, and it's just pi 3.14. And next, we will finally define Reynolds number, which we will have that equal to this expression, in which we have rho, the density, times V, which is literally right here above, times D, diameter, divided by mu. So now from this, we will want it to return this expression, which I will explain after I type it. I made a mistake right here. So we will have it return this expression, in which this NP dot sign determines the sign of Q, in other words, the direction of the flow. And here we have previous variables. And if you notice right here, this is the function we just defined previously. So all these functions and models are kind of starting to flow together, no pun intended. And then here we just have it divided by gravity at the end. So if we hit Shift Enter, no error so far, which is good. You like to see that. So now we are going to take a couple of steps towards the flow aspect of this problem. So we are going to create a function for flow. And for this, we will need the d head, which we just did. We will need the length, we'll need k, we'll need d, and we'll need ed. So for this one, we are going to create a variable called dhab. And as you can expect, this will be the absolute value of the d head. So we are going to have this equal to np.abs of dhead, if I could spell it. And what we are going to do is go ahead and add on to this So what this is pretty much saying is if dhab is less than 1 times 10 to the negative 10th, then we're just going to return the value of 0. Because essentially, if it's less than that, it's close enough to 0, we should count it as 0 rather than anything else. But then as you can see here, we have this np.abs from numpy yet again, and it will just take the absolute value of dhead. So now we are also going to make a variable called qguess, which is guess at the flow. And we are going to have this equal to np.pi, which again is just pi, times d to 2 divided by 4 and times np dot square root of, yes, I did that right, of dhab divided by k plus 4, yeah, times 0.01. All right, so for this, as you can see, we have this np dot square root, which is taking square root. And it just so happens that if you notice, we have this dhab. Well, since the absolute value is always positive, and these values are positive, well, then we're going to get a real answer, a non-imaginary number, which is the whole point of why we wanted to make this absolute value, essentially, so we don't get negatives and square roots. So now if we hit Shift Enter, there's an error. dhab is not defined. Let me look at this. Oh, shoot. Oh, I see. I think I see what's the issue. Oh, didn't want to do that there. Okay. Okay, that was what it was. Yeah, so this didn't have an indent, so kind of as outside of the code, so it didn't register that we had a dhab value because it was outside of our function right here. So yeah, that's why. All right, so now what we are going to do is we are going to, I didn't mean to capitalize that. We are going to create another function called f to 0. And all that we are going to need is q, a single variable. I know it's shocking, right? And we want to return two things from this. One is the d head, q, l, k, d, pd, and we want to subtract the absolute value of the d head from that. And we are going to create a variable, more like a sentence, for the resulting flow rate. And we are going to use the Newton, which is from up here. And we are going to have f(0) and the q guess. And we also want to return the sign of the d head times resulting flow rate. So pretty much what this is doing, we have the d head minus the absolute value of the d head. So this f to 0 is essentially, we are making this go to 0. And the whole point of this return is we are taking the sign of the d head, which could theoretically be negative, and we are just multiplying it by the resulting flow rate. So this could give us a negative flow rate value if the d head and resulting flow, if the d head sign is negative and the resulting flow rate is positive, or vice versa. It could give us a negative, or if they're both negative and both positive, then it will give us a positive value. So if we hit Shift Enter, no errors, that's good. So now what we are going to do, we are going to make a list of arrays that we are going to call pipes. If I could type. And essentially what we are going to do is we are going to have a list of arrays. And in the arrays, we are going to describe between which nodes the pipes run and things such as that. So for instance, this np.array, notice how it's np, also from the numpy, imported from this numpy. So, all right, now I can see. So we are going to have our first array from 0 to 1. And here we'll have the 1.5 and 1.5. And now we are going to have comma. And I'm going to separate them by hitting enter after each one, so it's not a massive line and they're kind of stacked, so we can actually compare them. So now we will have, it's really hard to see with this box. From 0 to 2. All right. There's going to be a lot of entries here because there are a lot of pipes in the problem. Okay, for 6 I missed a value because that array was just way smaller. Well, that list. Oh, hold on. Okay, that's weird. I don't know why it did that, but okay. So now we have our array of pipes. You know, we have it from 0, 1, 0, 2, 1 to 2, 1 to 3, 2 to 4, 3 to 4. So now what comes next is we're going to have one more array, which we call Z. And have our np.array, the list, and we are going to have 30, and then 0, 0, 0, 0. Yes, because what this array represents is the altitudes. So we have Z as the altitude, and the Python indexing actually starts at 0. So the values for node 0 is 30, because node 0 is the only one that's elevated. And we have 1, 2, 3, 4. And it works out quite nicely for us. So now what we are going to do is we are going to create a lot of equations in which we will use for the upcoming functions. And we are going to have things such as external P or external pressure for the nodes with external pressure. And we are going to have another array. And in this array, we're going to have 2e to the 5th, or 2 times 10 to the 5th, and then we're going to have 0. And we're going to have a lot more equations, and I mean a lot. So external nodes, we're going to have 0, 4, because if you notice, we have nodes 0, 1, 2, 3, 4, and this is 0 to 4, so it matches nodes. So then we want one called from nodes, and we are going to call upon the pipes array. Yes, there we go. And we will have yeah, 0. And we're going to just have as type np.int32. So what this is pretty much saying is the from nodes, when we have our pipes, we'd say, oh, the water flows from pipe 0 to pipe 1. So these from nodes are calling upon the pipes array right here, but for the 0th turn. And since indexing starts at 0, as I mentioned when referencing this array, this is the 0th turn. 0th term, that's hard to say. So, you know, we have from node 0, from node 0, from node 1, from node 1, from node 2, from node 3. So those are our from nodes. And now, since we have our from nodes, we need our to nodes. So you are going to see a very large similarity when it comes to typing this. So as you can see, this one, this one, 2 nodes, has a 1 here rather than a 0. Well, because we go 0, 1 when counting in lists. So this one term, these are all of the nodes something flows to. So for instance, the first line, from node 0, here is 0, to node 1, here's the 1. So it goes from 0 to 1. And now we will have, I'm just going to copy and paste this. Well, not that far. Copy and paste this, because we are going to be referencing back quite a bit. So if you notice in this one, we have a 2. This is the 2 value because these are the lengths of each of the pipes. So length of the pipe connecting node 0 to node 1 is 1.5. And now we have our K values. And guess what? It's almost, why did it go up the line? It's almost the exact same, except it's 3. So in indexing 0, 1, 2, 3. This last value is our K values for each of the pipes. So now if we make a variable called inPipes, I did not mean to have I. So what this will do is give us a number of pipes. And if we have pipe underscore ed, because if I typed it out like that, that doesn't even look like anything. So making one called pipe ed, and have np.full and have npipes. And if you notice, as I'm typing this, when I call upon the np.full, up here, it gives us the parameters. So we have the shape equal to inPipes, and the fill value equal to diameter. So next, I will have one called pipe D, which we will have np full again, and we will have in pipes. Oh wait, actually I mixed these up. This one should be D. This one should be ED. Yes. Yeah, because we want the relative roughness with relative roughness and diameter with diameter. So what's next after that is we will make one called in nodes, and we will have that equal to np.max. And if you notice, this np.max has numerous parameters and inputs and stuff. And what we want in it, I didn't mean to make another, is we want the pipes we want one for the node it's flowing to, has type p.int 32 plus 1. Because if you notice, there's one node that is not included. So I'm going to skip a part that we will include in this later, but go on. Oh, okay, yeah. So in this, it's just supposed to be shape. Nope. And for this, it's not supposed to be piped. It's supposed to be pipes. There we go. Okay, fixed it. So now what we are going to do is we are going to have yet another function made, and we are going to call this calc flows. And in this one, we will just need the heads, which is a little bit of foreshadowing here. So pretty much what this is doing is it's going to calculate the flow from each of the pipes. So we are going to have flows equal NP dot zeros for the end pipes. No, we are going to have this in nodes. And we are going to have this np.add.at net. No, that's for something else. So for that's for a different one. That's for when we want the calculating the net queue or net flow for this. So for this one, we want a for loop for I in range in pipes. And, and for all for loops, this for I could theoretically be any variable you want. I just chose I because it's what I've always used and was kind of taught to use. So we want the D head for this equal to heads 2 nodes. I need to capitalize the N or else I'll get a syntax error. Oh, sometimes this is confusing to use. And we want minus heads of the from nodes. And so for this, if you think about the D head is short for delta head. So it makes sense that it is the difference between the heads of the two nodes and the from nodes because it's change in head. So now what we want, so we're going to have flows I equal to the flow D head lengths for I, K for I, pipe D for I, and pipe underscore ED for I. So if you, and we are going to have it return the flows. So if you notice this for loop, we have for I in range in pipes. Well, in pipes is the shape of the pipes or how many pipes there are. So what this is pretty much doing is it's finding the difference for each of the pipes for the D head, and it's finding the flow and using this function for each of the pipes as well. So now we have that returning the flow. So if we hit Shift Enter, all right. And one thing that we now need to do is we need to have another function that I referenced earlier, as we want calc underscore NetCue. And we will use the flows for this. So NetCue is the net flow. We want it to equal np.zeros. And as you can see here, what it wants is a shape, flow, or order. And we will have it equal to n nodes. So this is for each of the nodes, since this n nodes is counts and does it for each of the nodes 0 through 4. So now what we want, np.add.add, we want NetCue, 2 nodes, from nodes. And now we want to do this, the same thing, np.add.add. Now, as you can see, we have at what indices as well. So NetCue from nodes in the second spot, and we will have the negative flows. And what we want to return is the NetCue, or the net flow. Shift Enter. All right, everything's still working. So now what we want is internal head guess, or a guess for the internal heads. We want that equal to np.mean. The heads, external nodes, Shift Enter. But if you see, there's something not defined. Well, up here, as I foreshadowed earlier, we are missing a little something. So what we want to define up here is heads for the heads of the nodes. So we want heads equal, I already put equal, I don't know why I put again, and p dot zeros for the number of nodes. But I hate when it does this. Oh my gosh. Okay, there we go. Finally got it. But that's not all we want to do. So we also want heads, but the external equal, I forgot to put the second half of the word, external nodes equal to the external pressure divided by rho divided by G plus the altitude of the external nodes. And now we also want the internal nodes because we will need this. We will have this as a list. Set range for a number of nodes. And we will subtract it from set range. Well, not range, just set the external nodes. So now if you see, our code works up until now. So now after having the internal head guess, we will also have an I really messed up spelling internal there. I still messed it up. All right, internal pressure guess, which we will just call internal P guess. And we will have this equal to the internal head guess, which is right above, is where we got it from, minus the altitudes of the internal nodes. I'm really struggling at typing decently fast and well. All right. And we will times it by rho and times it by G. All right. So now we will have our results equal to root, which, as you can see, for root we need the function, x0, arguments, methods, all that type of stuff. So all we really need is NetCue Internal and the internal P guess. Hit Shift Enter. I think I messed up my code. Yeah, so I got a little ahead of myself and actually completely forgot to add a function, which, as you can tell from this, will be called NetCue Internal. So let's go ahead and quickly make that. So it takes the internal pressure as the argument, internal P. And what we will have is heads, internal nodes. Oh, I did again. And we'll have this equal to the internal pressure divided by Rho divided by G plus the altitude of the internal nodes So now what we want this to return is the NetCue with calc flows and edits and for internal nodes. So if we hit Shift Enter, it works, it works, it works. Still something wrong. So it says something's wrong with this line. Alright, array is not broadcastable to correct shape. Let me make sure all of these are entered. Yeah, they are. Alright, so it's in Calc NetCue. It's right here. It's everything spelled right. We have our NetCue from nodes and negative flows. Everything looks to be spelled right. Make sure everything, is that, yeah, that's right. Those for I. That's where it's, this is where it's wrong. This should not be in nodes. this should be in pipes. And there we go, it works. So now, if we have result.x, hit Shift Enter, we have our array of the flow values. Well, not the flow values, just the results of the roots. And now what we will do is we are going to print our flow. I just combined flow and rates. All right, our calculated flow, we're going to have that equal to calc flows heads. And for I in range number of pipes, we are going to have it print. That's where the syntax gets a little weird, because printing syntax is always interesting, shall I say. We want from pipes I 0 This section needs to be a 1. All right. So now if we hit Shift Enter, calculate flows is not defined. Wait, hold on. No, I defined that here. Oh, forgot on S. There we go. So it's printing out almost the right stuff, except our values for the flow. So I'm not sure why it is doing that wrong. I will have to go back and check that later. So what this should display is the flow rates between each of these. Right now it says there is no flow rate between any of these, which there should be. So there is an error somewhere in the code. I'm not sure where though. Yeah, so what should happen is, print out for each of the pipes, which is why we say in range of in pipes, to make sure it repeats that many times. It should say from 0 to 1, the flow rate is 5 or whatever. I mean, technically, theoretically could be 0, but it's not supposed to be. So I'm not sure why it's not displaying that. But again, what this should display are actual numbers. So I will have to fix that later, because I'm not sure right at this moment why it is doing that.